The question we will be looking into today is how chemistry is used in forensic science. But before we can answer that question, we must establish two things. First, what is chemistry? It is the study of organic compounds and their structure, properties, composition, mechanisms, and reactions. Secondly, what is forensic science? Forensic science is the application of scientific principles, techniques, and methods to investigate a crime. They collect trace evidence, which includes materials that are often microscopic, such as paint, hair, fibers, fabrics, and adhesives. These materials are easily transferred between the victims, suspects, clothing, weapons, and other articles. To analyze physical evidence, forensic chemists use principles and concepts from chemistry. They look at the physical properties of a substance, which can be determined without chemical change, and chemical properties that can be determined only through a chemical reaction. The chemical properties are described through the reaction that occurs in the products that are formed. Forensic chemists go through the same scientific methods for each experiment that are taught to students in school. They observe the physical properties of a substance and make a hypothesis of what it might be, and develop a procedure and test to see if their hypothesis can be validated. Meet Melissa Valadez. She is a forensic scientist that works in the trace evidence section of a crime laboratory. The majority of her work is done in the lab using microscopes and other instrumentation. But sometimes she collects evidence from crime scenes and testifies in court to explain her procedures and conclusions to a jury. She has a Bachelor of Science in Chemistry and a Master of Science in Forensic Science. She has the skills to analyze hairs, fibers, paints, shoe prints, tire impressions, physical matches, and DNA. When asked about her favorite part of the job, Melissa said, "There is so much variety in what I do on a daily basis. Each case that comes in has its own story, and each item of evidence has to be handled in its own unique way. I get to do something different each day, and my knowledge base is constantly expanding. You just never know where each case will take you." Now, let's look into some specific tests and techniques that forensic scientists use and how chemistry is involved in it all. Let's start by looking at forensic toxicology. It is the investigation of toxic substances, environmental chemicals, and poisons. Specifically, it identifies illegal drugs and poisonous or hazardous chemicals and their role that they played in a crime scene. Forensic toxicology uses a combination of chemistry, pathology, and biochemistry. A sample must be taken from the body to test. It can be urine, saliva, blood samples, or hair strands in live patients, and internal organs can be examined in post-mortem bodies. Once a sample is obtained, there is a variety of different screening methods to be tried. If a forensic scientist suspects a compound involved contains a metal, they use chemical or thermal oxidation to leave the metal quantified in the inorganic residue. Then the metal can be detected and identified using the Rhine's test, X-ray diffraction, or emission spectroscopy. But let's focus on emission spectroscopy. We all know that matter is made of atoms. An atom can be represented through the quantum model, where protons and neutrons make up the positive mass in the center of the atom called the nucleus. Around the nucleus is a cloud of electrons, but it isn't just a random cloud of electrons, although it does look like it. Electrons move in orbitals that are precise regions of space at a certain energy level. And these energy levels have overlapping subshells, categorized by their shape, S, P, D, and F. So when electrons are in their lowest possible level, they are considered to be in their ground state. Electrons can be promoted to a higher energy level, an excited state, by absorbing heat. Electrons in an excited state eventually drop back down to their ground state and release photons, which are quantums of light energy. These photons can be measured on an emission spectrum, which is the spectrum of frequencies of an electromagnetic radiation emitted from an atom transitioning from a high energy state to a low one. Because each element has a different atomic number, each has a unique emission spectrum. This emission spectrum is what is used in spectroscopy. Forensic scientists use technology like a spectroscope, which separates light using a prism, allowing the spectra to be analyzed. They can compare the emission spectrum to an unknown substance to a known one. of each element to find a match. So let's picture this. A forensic scientist takes a sample from a person. They believe that it might have some metal in it, so she uses thermal oxidation to isolate the metal. Then the sample gets put in a spectroscope. The following emission spectrum is found. The forensic scientist compares the spectra and notices that it's a match to mercury. She can now draw conclusions that this person died from mercury poisoning. Now that we have went in depth with forensic toxicology, let's move on to forensic pathology. A forensic pathologist determines the cause of death of a victim, whether it was from natural causes and disease or foul play was involved. Their job is to answer the question, how did this person die, when it is not completely apparent. A forensic pathologist begins by doing a physical examination of the body to rule out any cause of death that is visible to the human eye, such as stab wounds, bullet wounds, or blunt force traumas. Next, a post-mortem autopsy is performed, where the body is dissected and tissue samples are taken, such as blood, fluid from the eye, urine, bile from the gallbladder, stomach contents, and solid organs. So imagine you are a forensic pathologist. You have been called down to a crime scene where a body was found. You arrive, and after doing a physical examination, your initial thoughts are that it is a drowning. The police want to know where the crime occurred, as bathtubs, pools, ponds, lakes, and the ocean are all possible locations. Therefore, to narrow down their search, you are going to test the pH of the water found in the victim's lungs. Pool water has a pH of approximately 7.4. Pond water is usually 7.2. A lake can be between 7.5 and 8, and the ocean has a pH level of 8.2. To determine where the water came from, you will calculate the pH of a salt solution. Sodium chloride is one of the main salts in the ocean, but it is a neutral salt because it is formed through a strong acid and strong base. But potassium sulfite is another common salt found in the ocean. It comes from potassium hydroxide, which is a strong base, and hydrogen sulfide, which is a weak acid. You then look at the conjugate base from the weak acid, which is sulfur ions, and how they react with water. From this balanced equation, you can see that the hydroxide ions are formed, which means the water in this person's lungs is a basic salt. But you want to find the pH, so you test the concentration of the sample and find it to be 17 moles per liter. You use an ice table to solve for the concentration of hydroxide ions. You use the approximation method. Next, you know that the Kb of hydrogen sulfide is 1.3 times 10 to the negative 13. So you sub this into the equation along with 17 moles per liter, which is the concentration of the sulfur ions. Now you can solve for the concentration of hydroxide ions, which is 1.5 times 10 to the negative 6. You can find that the pOH of water and then subtract it from 14 to find the pH, which is 8.2. So looking back, you can see that the ocean water has a pH of 8.2 as well. Now you can tell the police that the drowning occurred in the ocean, which will help their investigation. A unique type of forensic science is fire debris analysis. Fire debris is the scattered pieces of rubble and remains left after the flames have died. Arsonists often use an accelerant to start a fire. It speeds up a reaction, but is also used up during the process. This is not to get confused with a catalyst, which also speeds up the rate of reaction without being consumed in the process. It does this by changing the activation energy of a reaction. Activation energy is the minimum increase in potential energy of a system required for the molecules to react. So since the catalyst lowers the activation energy, the reaction can occur faster and reach equilibrium sooner. For a forensic scientist, it is important to obtain an adequate amount of samples to analyze. Information that they are trying to determine include where did the fire start, what is the ignition source, was an accelerant used, was the fire accidental or intentional. But let's talk specifically about accelerants. If a forensic scientist is investigating a crime where a person is claiming an arsonist burned down their building, they will examine the scene of the crime, specifically looking for accelerants, which would prove the fire was intentional. So types of accelerants include gasoline, fuel, kerosene, butane, aerosols, and other flammable solvents. There are irregular burn patterns in the fire debris that can indicate the presence of an ignitable liquid. If the forensic scientist finds a can of butane fuel in the corner of the room, now they can tell the police to treat this case as an intentional arson. So let's look closer at this butane. It will undergo a combustion reaction. A combustion reaction is an exothermic reaction, which means that energy is released when completing the reaction. This is because the potential energy of the reactants are higher than the products, so energy can be released. We will now move on to fingerprints. There are 3 different kinds of fingerprints that can be left at a crime scene: patent, impressed, or latent. Patent fingerprints are visible to the human eye, such as prints left on window glass or in blood, ink, or oil. Impressed prints are made in soft material by pressing down, for example in clay, mud, or wet cement. And finally, there are latent prints, and the ones that we will be focusing on today. They are not visible to the human eye, but can be still left on objects through physical contact as fingerprint residue. This is because sweat, salts, oils, and dirt particles are all over everyone's finger and imprinted and left behind when they touch something. So let's focus on perspiration, because that is what is utilized to create a visible fingerprint. It contains water, proteins, and acids, specifically acetic acid. But its formal IUPAC name is ethanoic acid. So IUPAC nomenclature is a universal systematic naming of organic chemical compounds. So eth represents the number of carbons in the longest carbon chain. The an part comes from alkane, which means all single bonds. And finally, the oic acid shows that the compound is a carboxylic acid and the functional group is a carboxyl. Knowing this, we can draw the compound. So we start off with a 2-carbon chain with a single bond and a carboxyl group. But let's get back to why this ethanoic acid is important to show the latent print. Powder dusting, which involves the use of fine powders, helps to visualize the latent fingerprint. It works best on dry, non-porous surfaces because the fingerprint residue needs to adhere to powder particles. Forensic scientists use different types of powder, but most common are made from fine carbon, iron, and aluminum. Once the powder is applied, it reacts with the acid to create a new substance with a dark purple-black color to it. The excess is dusted off and the print is lifted using tape. Now, we will move on to one of the most common things a forensic scientist will do, which is testing for the presence of blood. Blood found at crime scenes are not always from the victim, but sometimes the perpetrator. So using a blood to test for DNA is important in identifying everyone involved at the scene. There are 2 kinds of testing when it comes to blood: presumptive and confirmatory. Presumptive testing is a quick color test to see if the sample obtained is actually blood. Confirmatory testing is a more in-depth testing, where the sample is mixed with a chemical compound that reacts with hemoglobin, resulting in crystals under the microscope. And this sample can be used to look at the DNA and identify who it belonged to. Let's look specifically at confirmatory testing. But before we can get too far into it, we need to first clarify what redox reactions are. A reduction reaction is the gaining of electrons and a decrease in the oxidation number. An oxidation reaction is the loss of electrons and an increase in oxidation number. Now we can look at the Kastle-Meyer test, which determines if there is blood by using a chemical indicator, phenolphthalein. The presence of hemoglobin in blood, composed of an iron atom at its core, reacts with the hydrogen peroxide that is added to the sample, which is an oxidation reaction. Then phenolphthalein, which is not involved in this reaction, donates electrons to the hydrogen peroxide, which oxidizes itself into phenolphthalein. It is the phenolphthalein that is visibly pink. So if the sample does not turn pink, it means that blood is not there. Finally, let's talk about the chemical pollution of a crime scene. The crime scene is very important to forensic scientists. As you learned, the crime scene is full of evidence that needs to be collected and analyzed. In order to ensure that any evidence, like DNA, fibers, and fingerprints, does not get compromised, the crime scene must be protected from contaminants. Sources of pollution include rainwater, river water, oil, diesel, soil, and chemicals. Forensic scientists are required to wear protective clothing, footwear, gloves, and breathing masks to avoid bringing in foreign debris or chemicals to the crime scene. In conclusion, to answer our question of how chemistry is used in forensic scientists, it is used in many unique ways and diverse tests and techniques. Chemistry is a huge part of forensic toxicology, forensic pathology, biodebris analysis, lifting fingerprints, and testing for blood. Chemistry is an important aspect in people's daily lives and careers, especially in the field of forensic science.